right, so today we are going to finish up data transformations, and we are going, the homework is posted, homework 21 is posted, and it covers the whole part 14 on transformations of the data, transformations of variables to make the data look more linear. And so that's what we're going to finish up today. So we're, any questions on, and after that we're going to do logistic regression. So that'll be interesting. It'll be a nice, this is a nice segue into that because we're talking about log transformations, but logistic regression is going to be different. It's going to be when we're predicting a binary y. So far, all our y's have been quantitative. So let's finish up this part and go to the document camera. All right, so here's where we left off. We did a log transformation on the data on this, here, I can show it to you right here. Let's just go to the PC, and let me just show you what we're doing so you can recall. Okay, so we had this data on 34 land animals, dinosaurs, one cluster of dinosaurs, and then a bunch of mammals here. And before we did the log, it looked pretty bad. We're trying to predict the brain weight from their body weight. And then we have these giant body weight animals, these dinosaurs out here, that are just swamping the data. And if you look at the regression, if you look at the error plot here, it looks terrible. It has all these, you can't even see these little animals here. So what did we do? What we did was we decided to do this log transformation of both the y and the x. And at least we spread out the animals. So now we got a nicer, we can see them. We can see these little animals down here, and we can see these dinosaurs up here. And then we can see these bigger mammals up here, like the, etc. Okay, so we've got this, and we saw there's almost a very nice fit for the cat and the kangaroo. In the middle, there's nicer fits. But so let's look at the error plot now. And so we look at our errors. We'll show the errors here. And boy, you have to clear this out so you can see what you're doing. Sorry. Log. And then here we have the regression. And now if we show the errors now, they still don't look good. There's a pattern to them. But let's go ahead and work with this regression equation to make predictions before we do anything else to clean up these errors. Okay, so right now what we're going to do is we're going to make predictions and put confidence intervals around our predictions for this regression equation right here, even though we still have some work to do. So and then we're going to clean up these errors here in the chapter 40 and the following chapters and do the same thing again. All right, so let's go to the document camera now. So here we have that rounded regression equation. I showed you I rounded the numbers here, that's all. All right, and so we're going to use this equation to find the brain weight of a cat. I want to keep it simple now. We're going to have to make this more complicated to get rid of those errors. But let's just learn the procedure on transformed data in a simple regression. Okay, so let's say the brain weight of a cat, given the cat has a weight of 3.3 kilograms. Okay, so first find the log of the brain weight from this equation right here. So the log of brain weight is equal to 3 plus 0.32 times the natural, we're doing natural logs of the weight, which is that, 3.3. So we're going to get the log of the brain weight right here. And the log is, I just calculated that, and it's 3.382. No units because it's just an exponent. It's just a log. Okay, so now we want to anti-log this to get the actual brain weight, right? So if we anti-log both sides by raising e to the, exponentiating, we'll get the brain weight here, and we get is equal to e to the 3.382, which is equal to 29.43, and now we're in units grams. That was just the exponent. Okay, so that's our prediction for the cat. It's brain weight. Now, what was the cat's actual brain weight? It was in the plot. It's 25.6. So we go to the plot right here. And this is in logs, right? In logs, but in right here, it's just the actual weight is a tiny bit under. Let's look. The actual weight is 25.6, and we got 29.43. So what's the residual? Well, the residual is just, that's just the error. So it's how far above or below the actual is from our prediction. So it's our actual minus the predicted. All right, so our actual is 25.6 given, minus what we predicted right there is 29.43. So it's just a little bit below the line. It looked like it was really on the line. It's just a little bit below. This is a very small residual here. The cat is a little bit below the regression line. Okay? How about the human? Let's look here. The human's way above. The human has a big residual. The cat's just slightly below. Okay, so now let's do the human. And so we're just going to do the same thing with the human to find the brain weight of the human. We have to, our equation is in terms of log, so we have to do that first. So the log of the brain weight, I'm just doing the same thing, is equal to 3 plus 0.32 times the log of, this is the human that's on our graph, 62 kilograms, times the log of 62. Okay, and I did that, and I got 4.32. Just that's the exponent. So now we anti-log both sides, and we get the brain weight is equal to e to the 4.32. So you can see you're going to need a calculator on your next exam for sure. You won't be able to, so don't forget to make sure that you have a calculator that logs and anti-log stuff. Okay? And I got 75.24 grams. The weight is, don't get the weight, the body weight's in kilograms. Your brain's much smaller, so we put it in grams. Okay, so now, so the actual human's brain weight is much bigger than that. So that regression line didn't fit the humans very well. It didn't fit, because it was trying to, combine them. Even though it's much better after we logged, it's trying to fit all these dinosaurs over here. So it's kind of, just fits these animals in the middle pretty well, like the cat. But look at the human, far off. So we're going to have a big residual there. And the actual minus the predicted. This is the actual, much bigger than what we would think. And so that's a very huge residual. So we're going to take care of that by figuring, we're going to clean up those errors in the next chapter, but right now let's just work with this. I'm just showing you how to log and how to do anti-logs and how to build confidence intervals around log data, okay? So now I just want you to look at, okay, so we're changing, we want to change the log back to the body weight. And in general, note what's happening here. We did it, but you might not have realized what's going on here. That you see how you have these coefficients we have the intercept here, and then you have the slope here. Okay? So look what happens when you go from a log and you anti-log it. What happens is that this intercept right here and this slope become exponents, right? They become exponents in the actual variables. So here, this is your usual regression equation where you have, you know, an intercept plus this is the additive change for each increase, but it's in x. So if you go up 1 in x, this tells you how much you go up in y, how much you, but this is an additive change. Here it's going to become a multiplicative change. These all become exponents here, okay? So that's going to be, that's the big difference. So, well, maybe we should just do it out explicitly here. So if we did, what are we doing? We're taking this, I'm just copying this log of the brain weight. I know this is very simple arithmetic for math majors because you're so used to this, but some people haven't seen this since maybe 3 years ago or something, don't usually work with logarithms, and they're not intuitive to most people. So I'm just going to go through this. Okay, so here times the log of the body weight. So this is what we get. This is what's linear. It's a linear equation, right? But then when we change it back to our actual variables, because we're usually interested in the actual brain weight, not the log of the brain weight, right? So then we exponentiate both sides, and what do we get? So then this changes to brain weight equals, I'll go really slow here, E, I'm just raising, you know, E and taking just, okay, so then this changes to E to the 3 plus 0.32 times the log of the body weight. All right, so that's where we're at. And so now, you know, when you're adding exponents here, it's multiplication, you know, like 10 to the 1 plus 2 in the exponents would be 10 to the 1 times 10 squared, right? So this is e to the, so here we get this, we'll just write it again, is the brain weight is equal to e cubed times, now e to the, this is just multiplied together. I'm just going to, it's commutative, so I'll just put the log first, log of body weight, times 0.32. Okay, I just switched the order there. And I did that because you can probably see that this right here is just body weight. So now we get e cubed times the body weight to 0.32. So that's how you get this, these right here are the exponents. So make sure to check that. They're always going to be exponents, your intercept and your slope. Okay? And the one that's really matters is the slope for your x variable, for your variable here. That becomes an exponent right here. So some people prefer to work in log base 10 because it's more intuitive, because you just count how many zeros there are after the 1, you know, to get the log. So, so what would have happened if we'd done log base 10 instead of the natural log? What would have changed? Well, only the intercept would change. You'd still have this part being exactly the same. Only the intercept would change. So in our equation, this relationship would be the same. It would just be shifted. Your line would be shifted. It would be an intercept, just a shift. the slope would be the same. And that's just because when you do a change of base, you just would, if we wanted to do you want to see that worked out or not? You don't have to. Do you want to? No? Okay, it's just a change of base. Basically what you would do is you divide the whole formula through this formula right here. You would just, if you want to change, you just divide through by natural log base 10, which is like 2.303 or something like that. So you divide through by 2.303, 2.303, and you divide through, and then this intercept would change. But when you divide through by log, natural log base of natural log of 10, this just changes to log base 10 of body weight. I can just do that really quickly. So you could just, if you want to see it. So it's, if you just divided both sides through by 2.303, because that's log, natural log of 10, you'd get 3 over 2.303. That would change. Plus, you'd get 0.32 times the natural log of the body weight divided through by 2.303, and that is equal to 3 over 2. See, the slope changes, but you just get 0.32, and that would give you log base 10 of the body weight. And this would be log base 10 of the brain weight. It's just dividing through by that. Okay? So that makes it, you're not going to be tested on that. I just want you to know. All right. So now, all right, so now this is important, computing these confidence intervals for these transformed variables. Remember, we transformed these variables in order to get to make the plot linear, and then to get the errors around the regression line to be about normal. Let's assume, we haven't quite finished that process, but pretend we did. So assume our error assumptions are met. It's just easier to learn this on a simple data. Assume error assumptions are met, okay? They're not. We're going to make sure they're met in the next chapter. Okay, so pretend we did do that. Then we transform the variables in order to get the errors around the regression line to be about normal. This means that then we can use our standard deviation of the errors, or standard deviation plus of the errors, to compute confidence intervals. But they're going to be confidence intervals for the transformed variables. So we're going to then translate the confidence intervals back to the original variables. So it's a two-step process. All right. We do it in 2 steps. So we first just do the usual, compute the confidence intervals for our log, for our predictions for the log of the brain weight, and then we're going to, the second step will be translating those to the actual confidence intervals for the brain weight. Okay, so how do we do this? We do this as, let's just work with the normal curve instead of the t-curve. It's the same idea. So basically, remember, confidence intervals, it's like centered at 0, or if we're using the normal curve, between -1 and 1 will be 68% of the data, and between -2 and 2 will be between 95% of the data. And this is approximations. This is, it's more exactly 1.96, but let's just keep it simple. So we're going to say, okay, 68% confidence interval will be our transformed prediction, plus or minus 1 standard error, and 95 will be plus that prediction plus or minus 2 standard deviations for the errors. All right, so let's just do that then. All right, so we estimated the brain weight of a 3.3 kilogram cat to be, we did this first, remember we got the log of that, and we got it to be from the previous page. We did that. And by plugging in, what did we plug in right here for 33, right? Is that right? 3.3. And we got this to be 3.382. That's what we've already done, right? And then to get the estimated brain weight of that, we just exponentiated. Here's the log and then the brain. This is what we've already done. And we got 29.43 grams. So this is our estimated brain weight. And this right here is our estimate for what? The log of the brain weight. Our estimated log of the brain weight. All right, so we're going to work around this estimate first. We're going to put error bars around this estimate first. So let's do that. All right, to attach error bars to our estimate, we'll need to use, where's this coming from? 1.6. That's the rounded standard deviation of the errors. It's just coming from the previous page, rounded. Oh, okay? All right, that was given to us. But remember, okay, so 95% confidence interval for the log of the brain weight is just going to be what? Our estimate plus or minus 2 times the standard errors. So the 95% confidence interval, we're doing the log first because these errors were, this 1.6 came from our log equation, right? This is errors using the log equation, okay? So for the log of the brain weight is going to be this estimate, 3.382 plus or minus, we're just doing this right here, plus or minus 2, because we want 95% confidence interval, times 1.6. Maybe if I highlight things, it will be easier to see where they're coming from. So this 1.6 is the standard deviation of the errors. And this is just our estimated brain weight there. Okay, so that's all we're doing. So we're just going to do that. So this is 3.382 minus 2 times 1.6 is 3.2. And this is 3.382 plus 3.2. This is very old hat to you. And this is what I got. So these are logs, okay? Now, and it's just the usual thing. You take these two and average them and you get our estimate. It's symmetrical around our estimate, plus or minus 3.2. But now when you anti-log it, what do we do? Well, we just anti-log these. So we say e to the 0.182 to e to the 6.582. We're just anti-logging those. And now we get 1.2 to 722. And this is actually in grams. This is in no units and this is in grams. And the thing that I want to show you is that the confidence interval is symmetrical for the brain weight. For the log of the brain weight. If you average those two, you get our estimate. It's symmetrical. But if you average these two, it's not. We don't get our confidence, it's not symmetrical around 29.43. If you average those two, you get something much bigger than 29.43. So it's kind of symmetrical, but it's asymmetrical, okay? So, so it's because it's symmetrical, it's the geometric mean, no longer the arithmetic mean. So if you wanted to check this, if you wanted to, you would check that our estimate 29.43, check if it's the geometric mean, because now what it was symmetric around are exponents. So you check whether it's equal to that. Check that. And it should be. You can see this really easily because all I'm doing is this. Remember, this is the square root of what? E to the 0.182, which is that. So it's 3 point, here's where this is minus 3.2, but it's in the exponent. And then this one is e to the 6.582, but it's e to the 3.382 plus 3.2. And this 29.43 is e to the 3.382. So you can write it like this, and now you can really see why it happens. Because what are we doing? We have a minus and a plus here. So we're saying it's pretty obvious. Okay? So it's symmetrical. It's the geometric mean, not the arithmetic mean. The log, like you're used to. You're used to having, an estimate, and then you have symmetrical error bars. Well, these are very asymmetrical. Our 29.43 is much closer, it will always be much closer to the lower one than the higher one. Because look. Okay. So that's the idea. Any questions on that? Okay, so let's just highlight that though, because that's super important. Asymmetrical for the actual brain weight. Instead, it's the geometric mean. Okay. Now we're going to go back and clean up the errors. Okay, we're going to go back and we're going to look at this residual plot. And this is chapter 42. So now we look at this and we're going to check the assumptions about the errors. And why do we need these assumptions? We need them to compute standard errors, perform significance tests, and we should have used them. We shouldn't have done those confidence intervals like right here. That depended on normally distributed errors, and they're not. They're not. So now we're going to make them more normally distributed. All right. So when you make a scatter plot of the residuals, so here's the actual graph, and you can see that here we have log brain on the y and log body weight on the x. And you can see that there really seem to be two batches of animals. Like these that have a stronger slope, and these right here that have a flatter slope. So these are more, body weight has a much bigger effect right here on brain weight, or a bigger association than it does here. So there's a steeper line. There's a much steeper line here. Okay? And if you look at the error plot right here, the errors don't look independent. There's a pattern. There's a pattern to them. They don't look independent. As the body weight goes up, your errors, way up here, the errors are below. They have negative errors. So that means we're underestimating. We're overestimating. We're overestimating their actual brain weight. And here, we're underestimating it. And so it looks, here we're doing the same. We're only doing a good job. Here, right here in the middle, we're underestimating. On the ends, they're both negative errors right here. So it's only really doing a good job right in the middle for like the cat and the kangaroo. But, and also for this one animal right here. We'll have to figure out who that is. Okay, so there's a marked body right here, big body, surprisingly small brains right here. What do you think that is? And what do you think these are? Let's check it out. So let's go to the PC. Okay, so we're here, and let's see who these are right here. So these are all the dinosaurs. Who's this one that's right on the line? That's Tyrannosaurus Rex. So he has a surprisingly big brain for his body, probably because he was a predator, so he had to figure out how to hunt. These, I think these are, aren't these vegetarians? Tyrannosaurus Rex had those giant teeth, you know, he must be like a, so he's probably smarter than your average dinosaur. So he's up on the line here. And who are these? The elephants, the African, Asian, whoops, and the African elephant. Who's this? These are what, humans and elephants are very smart compared to their, you know, size of their bodies here if we do this. All right, and here's the cat and the kangaroo. And these are these little animals. All right, so now what are we going to do? What should we do? Any suggestions? What do you think? We have two groups. What do we usually do when we have two groups? We have these dinosaurs here. Don't you think we should split, like split on the dinosaurs? Let's try that. So let's choose a split, and we can choose a split on dinosaur. So here's 0, 1 for dinosaurs, there aren't as many, and 0 for non-dinosaurs, for the mammals. So let's do that, and what happens if we split the plots? What I want you to check is, does the correlation go up? Do our errors go down? Let's see. Yes, our errors go down. Our correlation is really good for, what happened here? Let's just do this again. Sorry about that, it doesn't look right. Okay, so here we go to the scatter. Let's do this again. We go to the scatter plot, but we've got the log and the log. Why do we have, oh, because we're showing the errors. I don't want to show the errors. Okay, so now what I want to do right here is we've split it. So this is level 1 of dinosaur and level 2 of dinosaur. So let's combine them, and we'll combine them into one plot, and we can see what's going on better. Okay, so we've got, now we've got a much stronger slope here. So that would indicate that we should do an interaction term, which would make things really complicated. But what if we force them to have equal slopes? So this is just playing around with data, looking at it. Okay, so now we can see that we have, let's look. We have a much better fit at level 1. That's 0 for dinosaur, that's mammals right here. We have a much better fit, and our errors have gone down, and we have a 0.957. We don't have a great fit for this, but they're all sort of clumped together. How much is it really going to change if we force them to have the same slopes? Let's try it. So if we force them to have the same slopes, it's really not going to change much. So we could add an interaction term if we really thought it would improve the fit much, but check it out. Look, it's not going to improve. Forcing the dinosaurs to have the same steep slope, they're all like in a clump here. They're not, they have a really nice relationship here, right, with the mammals, but the relationship isn't as good for the dinosaurs. So if we, no matter what we do with the dinosaurs, it's not going to really change things. Let's show equal slopes. See how we still get pretty much the same fit. So it's not worth it to add an interaction term, I would say. So now we have this, all right? And that looks much better, all right? So let's go back to our document camera. And this is really what you need to do. You need to really, just dive into the data, think about what your data is, what you're trying to do, and what works. And there's, okay? So this looks good. We realize it turns out these are dinos, okay? And these are mammals. And there's our cat again. That we got the really nice fit for. Okay, so now, so we really want to, looking at the errors, we saw that we only got close for the cat because it happened to be near the middle of the plot. That was the point. If we pick a small animal, like a hamster down here, we'd seriously overestimate the brain weight. And for a big mammal, like an elephant, we'd seriously underestimate it. Okay? In fact, for a big mammal, the systematic log errors at the ends are bigger than 2, bigger than a factor of 2. Look at this. These errors are huge. A factor of 2 in the logs. That means a factor of 10 in the weight itself. That's not good. So we want to do better. And since we have 2 separate groups, we can do a better fit. By what? By splitting into 2 groups. So let's do that. And that's what we did. So have we improved the fit? Yeah, definitely. Yes. Much nicer. The errors cleaned up? Yes. The errors look really much better. Look how much better these errors look. There's like no pattern to them. They look much, much better. And so now, here's the output for the multiple regression. We didn't look at that just then, but we could. And here's the output for the multiple regression. So we've included another variable. So what do we have here? We have 3 parameters here. We have our intercept. And now we have the log. This is the natural log of x1. And then we just have x2. We're not logging the dinosaurs. It's just a binary variable here. All right, and then we have our intercept. And our p-values look great. Everything looks really good. And our errors are nice. They went down a lot. Everything's nice here. So let's write the multiple regression. Let's just write it down. We can get it right from here. And we have the log, the natural log of the brain weight, is equal to this intercept, which is 2.257 plus 0.7263 times what? Times the log of the body weight times the log of the body weight. I didn't need these parentheses. This times that. And then what's our last one? What's this? Minus, it's not logged or anything, it's minus 4.833 times dinosaur. Now remember what dinosaur is. It's just a 0, 1. That's just going to change the intercept. And what is it? If you're a dinosaur, it's 1. And if you're not a dinosaur, which is a mammal, it's 0. And you see, that's what we want. It's just going to, we look down here, it's just changing the intercept. Okay? So if you're a dinosaur, you subtract off negative 4.8. You subtract off 4.833. All right. So that's all that's happening. And so is it the same as these 2 regression equations here? Well, sure it is. We can do it if you want. This is what we did before. We could just say, okay, for mammals we'll get, we should get that, of course, because dinosaurs is 0 and it drops out. So you just get this. That minus 4.833 times 0. Okay, so there we have it. And that's exactly the same as that one. And now this one, it has the same slope for dinosaurs. It just has a different intercept because we're just taking 2.257 and subtracting off 4.833. So we get the same thing again. I can write it again. 2.257 plus this part. We're just subtracting off this. All right, and so what do we get? And of course, this is the log of the brain weight. That's what we're talking about, equals that. So what do we get? We just subtract those two, and we should get exactly that equation up there. Negative 2.577 plus 0, the same slope, times the log of the body weight. So yeah, we do get it. Okay, and if we included an interaction term, it would have cost us, it would have been way more complicated, and we didn't need it. Okay, so that's pretty much it. Now we can look at what we should have done before, is look at look at that to see if the errors are normally distributed. We saw that they didn't have any pattern here, and now we want to make a little histogram of them, and they look pretty normal. Most of them are around 0. There seem to be bigger ones well, a few more bigger ones. It's not quite normal, but it's very close to normal. So that means we can go ahead and we can do everything. We can perform significance tests on the model, everything. Okay. So any questions on that? None? All right. So now I just want to interpret these coefficients in the log model. Okay? So what's the multiple regression equation in terms of logs translated to original variables? We don't have to write it again. We have it right here. So this part, this is just this one, and that's that one. I don't know why I wrote it twice. Okay, so here we have it. We've already done that. Now, what's it saying? How do we interpret this? I just want to interpret these coefficients here, what they are. Okay, so first let's look at the dinosaur. Remember, dinos are equal to 1. When you have a dinosaur, you put a 1 in there. And no dinos, non-dinos, which are mammals, are equal to 0. So we have a negative here. We interpret it because dinosaurs, how do you interpret this? It's negative. Why? It's probably pretty obvious. Because dinosaurs have smaller brains relative to their bodies than mammals do. We're controlling for body weight here. So smaller brains relative to their bodies. Compared to mammals. Now, what if we had coded it the other way? We could have chosen to code the mammals as 1 and the dinosaurs as 0. Then this would just change sign. That's all. It would be positive. That's all that would happen. All right. And let's just remember that these beta 0, these coefficients here all become exponents. Okay. So, and for mammals, what did we get? Remember, dinosaurs is a binary variable, so the equation simplifies from mammals to what? So this equation right here for mammals just simplifies to what? This is super easy. Times what? That's going to be a 0 there, so it's going to be e to the 0, which is just 1. Just put a 0 in there, and that's just 1. And then for dinosaurs, you're going to get exactly the same thing. Exactly the same thing. But now you have e to the minus 4.833 times 1. And that right there that right there is equal to what? That's, you don't know, I just calculated, it is equal to 0.008. It's equal to 1 over 125. So basically, mammals have, you know, for the same body weight, mammals, our predictions saying that mammals have 125 times heavier brain than dinosaurs, where dinosaurs have 0.008. Okay? So the brain weight of dinosaurs is 0.008, or 1/125th of the brain weight of mammals. And where does that factor appear in the regression equation? In the regression equation, the log equation, that factor is right here. We'll circle it. So basically, it's the slope for dinos in the log equation. So what we want to do here is we want to raise that slope, so we could say e to that slope, e to the minus 4.8, 33 is equal to e to the slope for dinos in our regression equation. So that's what that is. Okay, so so you can think of it like what? You predict a 90-kilogram mammal to have a brain weight of what? Mammal to have a brain weight of what? For the mammal, we'd have the brain weight, we'll just use our equation, equals e to the 2.257 times 90 raised to the, 0.7263. And I got about 251 there. So now, if you know that, what's the brain weight of the dinosaur going to be? Just 120. It's going to be 251 times 1 over 125, which is about 2. It's because for the dinosaurs, you're going to have the same exact thing. The brain weight, you have this same thing, but now you're going to multiply, by 0.008, which is the same thing as 1 over 125. Okay? And so this additive change becomes a multiplicative change, that's all. And the multiplicative change is e to the slope, e to whatever that slope was. So it's a multiplicative change of, in this case, it's equal to e to the negative 4.833, which is 0.008. Or you could divide by that and say just divide by 125. Okay. Any questions on that? Kind of boring, isn't it? Really boring. And for those of you who logarithms are just like so easy, it's just like addition and subtraction or multiplication, I'm sorry to bore you, but I know that a lot of people haven't had them for a while and are a little bit rusty. Okay, and a lot of people, myself included, don't really think naturally in terms of logarithms, intuitively in terms of logarithms, which is why I like to translate it back. I'm sure some of you do think into, it's just a matter of practice. People who work with them a lot. Physicists, all that I know, I'm married to one, always think in terms of logs. So I know a lot of people intuitively think that way, but most of us don't. All right, now correcting heteroscedasticity. So there's another, so what we've done so far, we haven't looked at violating this assumption of unequal variance across a scatter plot. And this happens a lot with our own data. Like if we get these on lots of surveys, I ask how much do you party and how much do you drink, and we get a very strong correlation, but it has this fan-shaped, like this. You can see it's fan-shaped. The errors are bigger because you basically, because it's cut off at 0 here, you can't have negative drinking. So how do you correct for that? When you have a notice how the errors increase as x increases, so that violates one of our assumptions. And why does it even matter? Why is this a problem? It's a problem because this is going to affect the slope more. When you have a lot of variance around here, your standard, rather than in the middle, it's going to affect the slope. So it's going to affect the errors around the slope more. Why is this a problem? Because variance of y at extreme values of x affects the slope more than in the middle values. So, if you had the fan shape the other way, it would be just as much a problem. In the middle, it's not so much a problem because it's not going to change. Big variations at the ends are going to change the slope more than big variations in the middle. Okay, so the most common way to correct this is what? Is taking square roots, and that's what we're going to do. So these logs, the log transformations are extremely common, and the square roots are generally used to correct this fan shape problem in the errors. So let's just see how that would work. So you take square roots of both sides, and it cleans it up. It cleaned it up better. How did R change? R changed from, it was pretty strong before, but it got stronger. It changed from 0.77 to 0.82, so it went up. And what's our regression equation? You can just copy that down. It's just the square root of drinks. This is really simple. Is equal to negative 0.1893. Sorry, this real data's annoying because the numbers are, there's all these digits you have to write down, times the square root of the party hours. And this is predicted. We'd have to add some errors here, and there's our standard deviation of the errors. Okay, so how many drinks per week does the regression equation predict for someone who's 25 hours? So you just say, okay, square root of drinks is equal to negative 0.1893 plus 1.083 times square root of 25. And what did I get? I did that, and I got 5.2. So, not drinks. They didn't ask for drinks. They asked, we have to do the square root of drinks to get the drinks, right? So, and that's not very, it's kind of silly to keep it in square roots. Who's going to think of drinks in terms of square roots? So got to cut down on my drinking. I drink about a square root of, something. It would just be so weird. Go to a bar and you say, hey, I'll have like a few square roots of that. Okay. So anyway, so you want drinks. So drinks is equal to 5.2 squared. This is really easy, and that's 27, and that seems about right. It's about, what was our equation to begin with? It was about for each additional party hour, you drink about one extra drink on the average, which sounds about right. You're at a party, you're probably, each hour about a drink. So that makes sense. Now, so that's in drinks. And this, just to show you how ridiculous it is, it's in square root of drinks. So now, because the confidence in these errors, we had to clean up the errors, so this was calculated in terms of square roots, so it's going to be symmetrical around the square root of drinks, but not around drinks itself, so we have to do the two steps again. So the first step one, is you just take your estimate, which is 5.2. So this is a 95% confidence interval, and you just have to start with the transform variable for the square root of the drinks. And that is the 5.2 plus or minus 2, because we're just going to estimate it with 2, whatever we got here, 1.0, I'm just going to round it to 1.06. So we can do this in our heads. That's just so you don't get confused what I did here. That's the same. I just rounded it. Okay, and then step 2 is going to be what? Now you want the 95% confidence interval for the drinks. And don't do this. Don't say, you can't say, I know you'd be tempted to say 27 plus or minus, and then just square that. You can't do that. You have to get the endpoints and square them. So we'll do that. So 5.2 minus 2.12, and we get 3.08. That's what that is. All the way up to 5.2 plus 2.12, so that's 7.32. So those are our endpoints. Because it's not going to be symmetrical. You can't say 27 plus or minus this squared. No, it's not the same thing. You have to do this. And now you get, then you say 3.08 squared to 7.32 squared. And you get 9.5 to 53.6. You see, it's not 27 plus or minus anything. It's not. It's an asymmetrical confidence interval. All right, so this is step 2. And so note the confidence interval, but asymmetrical for drinks. And 27 is closer to the lower one. All right. Now, that's it. Can we just go home? That would be so nice. How did that go so quickly? It seemed like forever. It seemed like one of the most boring lectures to me, but probably that's why it went faster. Maybe I just had no asides to say because there was nothing to say. It was just arithmetic. Okay, so any questions? We could continue on with this, but let's not. Let's just enjoy the weekend and see you next time. And you're ready to do all the homework for Monday right now. You might as well just do it. It will be pretty easy, and you'll be done. Oh, you have time to do the R bonus because you really don't have much work. So you can do an R bonus, which will take you a while, probably as long as the homework. Maybe not as long as the homework, but a while. Okay. Have a nice weekend.